topologically conjugate. So the first thing we want to do is understand this question. So I will define to you what the earthquake flow is, what the Teichmüller horocycle flow is, and I will also try to explain why this question is relevant historically and also intrinsically. So that's what we'll start with. I'll try to explain to you what the earthquake flow is and what the Teichmüller horocycle flow is, and then we'll move on to the question and to a bit more of history. Throughout this talk, I'll always denote by mg. Is going to be the moduli space of genus G hyperbolic or Riemann surfaces. Yeah, so the space of all hyperbolic surfaces or Riemann surfaces by uniformization. And what's going to happen is that each one of these flows, the earthquake flow, is going to be more natural from the hyperbolic perspective, and the Teichmüller horocycle flow is going to be more natural from the Riemann surface perspective. So I'll need to use both points of view during the talk. So maybe let me get started and start talking a bit about the earthquake flow. So here's what I want to do. I want to give you first an example of the simplest orbit of an earthquake flow, and this corresponds to Fenchel-Nielsen twists. This is what I've pictured here, but let me describe to you in words what a Fenchel-Nielsen twist is. So a Fenchel-Nielsen twist is a deformation where you cut a hyperbolic surface, along a simple closed geodesic, and you reglue with a twist. Yeah, like in this picture here, what we're supposed to think is that we're cutting along the red geodesic over there, and then we're regluing back with a twist T, which is measured in terms of units of hyperbolic length. Yeah, so originally this blue arc crossed sort of perfectly through the red curve, but now that I've twisted, it sort of has been sheared to the side by a certain amount. So that's what a Fenchel-Nielsen twist is. You cut and then you reglue with a certain twist. So in some sense, what we end up getting is for each simple closed geodesic, we get a one parameter family of deformations. Yeah, the amount I twist is the parameter. And in some sense, how we're going to think about this is that the hyperbolic surface is going to be like a base point. Surface is going to act like a base point, and then the simple closed geodesic is going to act like a direction for the deformation. And this is going to be like a direction. Yeah. And the point is that Fenchel-Nielsen twists are nice, and maybe let me say that you can also define them for geodesics with several components. You can also weight the components, and that's going to change the speed at which you twist. You can generalize them a bit more, and we'll say a bit more about that later. But even with that more general situation, the problem is that we don't seem to have the structure of a bundle. And in our heads, we would like the example we always have of flows is some flow on the unit tangent bundle of a manifold. And here we would like to have a similar picture. We want a flow on sort of a unit tangent bundle over moduli space. So the question then is how to extend these deformations or this picture here to a bundle. Yeah. And extending this idea of twisting deformations for hyperbolic surfaces to a bundle will require introducing an object which is a bit unwieldy in some sense. It's at first approximation, it's hard to understand, but let me try to explain it in the simplest terms possible. So what we would like is certain objects that interpolate between closed GD6, simple closed GD6, and those objects are what are called measured geodesic laminations, if you haven't heard about them. And these objects are gonna act like a generalized locus along which we wanna shear our surface, sort of in the way that we did with Fenchel-Nielsen twists. But they're gonna be given by two pieces of data. First, we're gonna have a closed set foliated by disjoint simple GD6, like the one you see on the picture here on the right. Yep, you have a surface and you have this set foliated by disjoint simple GD6, and you're also going to have a this object is going to be carrying a fully supported transverse measure. Yeah, let me not say the complete definition of a transverse measure, but what it should be is an assignment that to every arc that's transverse to your lamination, to this geodesic lamination, it's assigning a measure. Yeah, so for instance, to this arc, it would assign a certain measure, and that measure has to be compatible with certain basic operations like splitting arcs into pieces, into countably many pieces, or isotoping the arcs respecting the lamination. It has some basic properties that we won't really need to use, but let's say that that's what we have. And at least to a certain degree of approximation, the role of this measure is that if I'm a person standing here in A, and I have a friend standing here in B, and I apply this earthquake flow, the amount I'm seeing this person sort of veer to my right should be equal to the transverse measure of this arc. Yeah, that's sort of why we want to have a transverse measure, because it's going to be a measure that's going to quantify the amount we're shearing at each step. But we're not going to need to go into too many details about measured geodesic laminations. Let me tell you what's important for us. For us, it's important that they fit into a space, which we call the space of measured geodesic laminations. Geodesic laminations on a genus G surface, say G bigger than or equal to 2. And this space we should always think about as an interpolation between simple closed geodesics. Yeah, the points in this space are some sort of continuum in which our simple closed geodesics sit in with some density properties, but the important thing is that there's some natural way to interpolate between geodesics, and that's what these laminations are supposed to be. Yeah. The only thing we're going to use is that this space exists. From now on, I'm never going to use like a specific picture of a lamination. I'll just use some properties about densities of simple closed curves. So just think about it as a continuum where the simple closed geodesics sit in. And once we have this space, the idea going back to work of Thurston and Kirchhoff is that we can have a bundle, which we'll denote by P1mg, which is the bundle of unit length measured geodesic laminations over moduli space. So better said is pairs x lambda, where x is a surface in moduli space and lambda is a lamination. And the length of lambda with respect to x is a unit. I haven't told you how to define the length of a lamination, but I hope that given that I told you these are objects that interpolate between simple closed geodesics and simple closed geodesics have a notion of length, I hope that you can believe me that there's a way to define length of a lamination. This definition also uses the transverse measure and all the structure they have. But for now, we think of this space of this bundle of laminations where we pick the ones that are unit length because we're thinking about like a unit tangent bundle, sort of. Yeah. And the point is that not only do we have a bundle, but we also have a flow and the flow is what we call the earthquake flow. So we have a flow, which we're going to denote by E, from this bundle back to itself. And we call it the earthquake flow. And the way it acts is that if you apply the earthquake to a point x comma lambda, what you're going to do is you're going to twist along lambda for time t. So you're going to twist your surface along lambda for time t, and you're going to leave the lambda guy by itself. Yeah, and this is supposed to extend continuously from Fenchel-Nielsen twists. Yeah, so in some very precise sense, as it happens that you can approximate any point in this completion by weighted simple closed geodesics for which we have a well-defined twist. And then this earthquake flow is just supposed to be the continuous extension of that. The content here is that there exists a continuous extension that's completely non-obvious, but I'm asking you to believe that there is. Yeah. Any questions about the earthquake flow? Okay, so if we're good with the earthquake flow, and I know I've just been kind of abstract and told you basically the picture I want you to have in your head, it's a flow that extends Fenchel-Nielsen twists to a natural bundle of objects that interpolate between simple closed geodesics. That's all that I want you to keep in mind. The other flow that was involved in our original motivation was the Teichmüller horocycle flow, and that will be a bit easier to define, especially if you came to the talk last week. So you might recognize this picture over here. So this flow, the Teichmüller horocycle flow, is more natural from the point of view of conformal geometry. So it's gonna more naturally act on Riemann surfaces. So let me remind you what a quadratic differential is. So this picture here is going to be the information of a Riemann surface together with a quadratic differential. And what is this picture? Well, this picture is just a polygon on the plane with pairs of sides which have been identified by translation, like the red sides, or translation and 180-degree rotation, like the blue sides. Yeah. And as we mentioned last week, these pictures encode a lot of information. They encode a topological surface because you can carry out the gluings, you're going to get a surface. And they also encode a Riemann surface because the operations that we considered for the gluings are all holomorphic. Yeah, translation is holomorphic, 180-degree rotation is holomorphic. So we're good with that. And as I told you last week, I asked you to believe me that the vertices you can handle and it's fine. You get a structure of a Riemann surface. But it's a bit more than the structure of a Riemann surface. Is a Riemann surface together with it being represented as this polygon. And what that tells us is that it's going to prescribe a one-parameter family of deformations. Family of deformations, similar to the ones we mentioned last week. Last week we spoke about the Teichmüller geodesic flow, but now I want to speak about the Teichmüller horocycle flow. And what you do here is the family of deformations. You take your polygon and you apply this unipotent matrix to it. And what this is going to do is sort of shear the polygon horizontally. Yeah. That's all what the deformation is. And this transformation is highly non-conformal. So you can expect that as you apply and you flow more and more, you're starting to see different Riemann surfaces. Yeah. So that's what the Teichmüller horocycle flow is. And at the end of the day, we can assemble it also into a bundle. We consider the bundle of all, this is the bundle of, let's say, unit area quadratic differentials over moduli space. And on it, we consider this flow, which I like to denote by U, which is the Teichmüller horocycle flow. Yeah, this is the Teichmüller horocycle flow. Yep. Any questions about this definition? Okay, so now we have two flows, which is great because that's sort of half of the question. We have the earthquake flow, which we constructed by continuously extending from Fenton-Nielsen twists to all measured geodesic laminations. And we also have this Teichmüller horocycle flow, which acts on quadratic differentials. And sort of historically, people started noticing that these flows seem to have a lot of similarities. So both come from an idea of shearing. In one case, you cut and reglue with a twist. In this case, you literally shear by applying a unipotent matrix. Both had been studied in analogy with unipotent dynamics. Another similarity is that both were Hamiltonian with respect to natural symplectic structures, and both satisfied certain non-divergence properties, which were quite strong. And so people started noticing that they had several similarities. And then the question is, are they related at all? And that's already an interesting question, just from the point of view that one flow is defined in terms of hyperbolic geometry and the other flow is defined in terms of conformal geometry. So this is sort of a deep question, like, is there a relation between these two types of deformations? And let me tell you the first answer to this question. So this is a theorem of Mirzakhani from 2008. And the theorem says that the earthquake flow, and Teichmüller horocycle flows are measurably conjugate. Yeah. So this means that on each of these bundles, we can find natural measures, Lebesgue class if you want, which if you forget about a measure zero subset of points, you can find a measurable map between these two bundles, which conjugates the flows. Yeah. And this is sort of a big achievement in some sense, as I was saying before, because you have this hyperbolic world where you have the earthquake flow, and you have this conformal world where you have the Teichmüller horocycle flow, and then sort of magically, and let me say that the measurable conjugacy is absolutely non-obvious. Sort of magically, they end up being conjugate. So in general, when you work in surfaces and Riemann surfaces, you notice that the conformal and the hyperbolic world are relatively hard to sort of friend up. And in this case, it turns out that they're quite friendly to each other. Yeah.
Can I ask a question?
Yep.
In these types of statements, does such a map preserve the bundle structure, or is it just like, forget the bundle structure, you just have this space with the flow and there's some...
Yeah, so that's a very good question, because actually to build the map in this case, the map that Mariam builds actually forgets the bundle structure.
Okay.
Yeah, so you're gonna take, say, a surface together with a lamination, and you're gonna map it to a surface with a quadratic differential, but those two surfaces don't need to be the same. They're actually gonna have different conformal structures. Mm-hmm.
And in particular, you might send one surface with two different laminations to two different surfaces with two different quadratic differentials.
Yeah.
Okay.
Yeah, you might send two surfaces, the same surface. I mean, yeah.
Like one fiber gets spread out.
One fiber gets spread
fibers.
out over multiple fibers. Yeah, exactly.
Okay, thanks.
Mm-hmm. Any other questions? Okay, yeah, so these conjugacies are kind of wild. They don't preserve the bundle structure. Maybe let me also mention recent work of Calderon and Farr, of which Aaron is, I think, gonna mentioned in his talk. So this is very recent, but it turns out that you can extend Mirzakhani's conjugacy to a natural bijection. So it's a map that's defined everywhere, but it turns out that the map is still measurable. Yeah, it's not continuous, but it's defined everywhere. Like you can make sense of this conjugacy at every point. But yeah, you see this, and maybe then you start asking, well, these flows are measurably conjugate. The conjugacy that has been built is not continuous. That's something that you can show. Is it the case that they can be topologically conjugate through another conjugacy that you can be more creative and you can come up with? Or is there something intrinsic of the flows that doesn't let them be topologically conjugate? Yeah, that doesn't let there be a continuous conjugacy between the flows. That's sort of the question that we have in mind. And here's the theorem that I want to talk about, or the theorem that's going to motivate this talk. And this is a result of myself and Alex, right? From 2021. And it's that the earthquake and Teichmüller horocycle flows and Teichmüller horocycle flows are not topologically conjugate. Meaning there is no continuous map between these flows, continuous bijection homeomorphism that's going to preserve the orbits of the flow that's going to conjugate one flow to the other. Yeah. And so this means that there must be something intrinsic about the flows, some property that these flows have that let you distinguish between the earthquake and the Teichmüller horocycle flow. And that's what we want to look at. Yeah. Any questions about the statement? Okay, so I'll tell you what the property is, but the property has to do with symmetries. So at the end of the day, what these flows are going to have different is that one of these flows is going to have a lot of symmetries and the other one is going to have no symmetries. So what do I mean by this? So let me tell you what the symmetries of a flow, let's call it E, let's denoted by ET from X to X. This is just some general flow, not the earthquake flow. I just want to define you what the symmetries of a flow are. So you can think about different categories of symmetries if you want to be more restrictive, less restrictive, and so on. So perhaps the most basic one is the centralizer of the flow. So an automorphism belongs to the centralizer of a flow if it commutes with the flow. Yeah, if the flow composed with the automorphism is the automorphism composed with the flow. Yeah, this is sort of the most simple, or if you want most restrictive idea that you can have of a symmetry. Yeah, something that commutes with the flow. Another thing that's slightly more general is the extended centralizer, where you allow the automorphism to reverse the time of the flow. So something like there is some parameter which can be plus minus 1, such that for every time you have the same thing as above, but with a time reversal. So you allow yourself to reverse time, optionally to reverse time. If epsilon is equal to -1, then this automorphism does not commute with the flow, but it conjugates the flow to its time reverse. Yeah. But let's be even more wild and consider even a larger group of symmetries, and that's the normalizer of the flow. And this might at first seem a bit weird, but let me write the definition and I'll explain where it comes from, and then it'll be more natural. These are automorphisms that not only can they reverse the time, but they can also dilate it. Yeah, so these are automorphisms where there exists some parameter which tells you if you're flipping the time or not. There exists some parameter which is telling you how much you're dilating time, and such that the following identity holds: e to the t composed with f is equal to f composed with e to the epsilon exponential of 2st. And you might recognize here on this side an identity, and this is the reason why one defines the normalizer this way, which one can see in SL2R. Yeah, if you take the diagonal matrix e to the s, e to the minus s, and then you take the unipotent 1t1, and then you take the inverse of the diagonal matrix, this conjugation is literally equal to e to the 2st, and then a 1 there. Yeah. So this normalizer is defined to account for this. A flow has an automorphism normalizes if it might possibly not commute with the flow, but it dilates its time. Yeah. That's what this is supposed to mean, and it happens in the same way that it happens for SL2R. And so the theorem that we actually prove with Alex is the following. So what we show with Alex is that this is in last year, is that the earthquake flow is strongly asymmetric, and by that what we mean is that, let me just write it, asymmetric, and by that what we mean is that its normalizer is equal to the smallest it could be, which is the flow. Yeah, the maps of the flow always belong to the centralizer, to the extended centralizer, to the normalizer. So that's the smallest these groups could be, and what we end up showing is that for the earthquake flow, the normalizer is as small as it could be. It's just the flow. Yeah. And right away from this theorem, you can see that this question about conjugacy follows right away. Because the earthquake flow, we're saying according to this theorem, has no normalizer, but you can right away see that the Teichmüller horocycle flow has automorphisms in its normalizer group. What are they? Well, here you would just apply this matrix, this unipotent matrix. Now just consider applying a diagonal matrix. And that's going to be an automorphism of this bundle that's going to belong to the normalizer of the Teichmüller horocycle flow. Yeah, just because it's defined exactly by multiplying matrices in SL2R. So that's the fundamental property that's telling you that these flows are different. The Teichmüller horocycle flow, or the transformations that we do in conformal geometry, tend to have this property that they're easy to reverse. They have symmetries, you can speed them up, but it turns out that when we work in the hyperbolic world, all that symmetry gets lost and you have nothing to graph from. Yeah.
Elementary question, Francisco.
Yep.
Is a reparameterization of the flow, does that count as a topological conjugacy?
You would need a transformation that reparametrizes the flow.
I guess I think what sometimes people talk about reparameterizations where it's like it's a different flow, but the flow lines are the same, but the speed at which you move along the flow lines can be different. Is that's not
that's more like
that doesn't have to be a topological conjugacy. So yeah,
that doesn't have to be topological conjugacy. Yeah, I guess that's more called orbit equivalence sometimes.
Orbit equivalence. Okay.
Yeah, you have some way of mapping the orbits of one to the orbits of the other.
Okay, so that's weaker. And I guess is this are these two flows orbit equivalent at least, or it's just a different question?
I mean so the bijection of Calderon and Farr certainly preserves the orbits, but the point is that it's not continuous. So
I see. Okay.
So again, it lacks some sort of continuity there. Yeah.
Okay. Yeah. Cool.
Nice. Okay. So what
I
I want to do, yeah.
Is there something analogous to the Teichmüller or geodesic flow for the earthquake flow? Something that, I mean, I guess I want to think, well, you have this measure conjugacy, but you don't have a topological conjugacy. So maybe there's something analogous to the.
Yeah, so there is an analog, which is, it's a bit tricky. It's called Thurston's stretch flow.
Oh, okay, yeah.
But the point is that it's sort of not defined everywhere. It's just defined when your locus, your lamination that you're stretching along is maximal. And I think the work of Aaron and James Farr extends this a bit, because you now look at orbits of the diagonal action and they give you new orbits that are geodesics for the Thurston metric. But yeah, it's a tricky flow to study. Yeah.
Yeah. Okay.
Okay. So what are we going to do now, or what are we going to do for the rest of the talk? I already gave you the punchline, but I want to explain at least some ideas that go into the proof, because I think they're already interesting. There's a couple of main ideas that I would at least like to get to. But what I will like to outline today is I want to explain to you why something simpler than the total proof. I just want to explain to you why the normalizer reduces to the extended centralizer. Yeah. And even more simply, I'm going to consider a transformation from this bundle to itself, satisfying the identity of being a normalizer, so something like this, without time reversal to make our lives easier. And I'm going to show to you that S must be 0, and that's the same as being in the centralizer. Yeah. So what we will do is we will reconstruct F little by little until reaching a contradiction. Unless the parameter S was equal to 0. But if the parameter S is equal to 0, then we have a transformation of the centralizer. Afterwards, showing that a transformation of the centralizer is an element of the flow is a completely different argument, but let me not do that for this talk. At least let me point out that already knowing that the normalizer is equal to the centralizer tells you that the earthquake flow is not conjugate to the horocycle flow. Yeah, because the horocycle flow does have a non-trivial normalizer. Yep. So what are we going to do then? Basically, what we are going to do is we're going to suppose that we have a point y mu, which we get as an image of a point x lambda after applying the conjugacy. And I'll try to reconstruct facts about y mu little by little. And there will be a point where all the facts cannot assemble together to give you a coherent picture. So for this, we're going to use 3 sets of tools. And in some sense, it's the only tools you can have given that you have a topological conjugacy. So the first thing that we want to look at is the minimal sets of the flow. And I'm going to tell you what these are and how we classify them. We're also going to use the curve complex to leverage a bit more information than what minimal sets give us. And then at the last stage, we're going to want to get very fine with our information. And for that, we're going to look at periods of orbits. Yeah, those are the 3 things that we're going to do. And to exemplify a bit how these results look, or what's the flavor of this reconstruction, what's going to happen is something like, we're going to see that if lambda is a simple closed multicurve, and perhaps this step is the most important of all, if lambda is a simple closed multicurve, yeah, a curve with several components, or a multi-geodesic if you want, a geodesic with several components, then, or if and only if actually, let me just write if and only if, mu is a simple closed multicurve. It'll be even more stronger if this curve has k components. This curve will also have k components. So this map is already sort of, this conjugacy is forced to be rigid in a sense. It's forced to map multicurves to multicurves. That's sort of a first step in reconstructing it. Afterwards, we're going to show something like, without loss of generality, you can assume that mu is proportional to lambda. Yeah, they're not only of the same, they don't only look the same number of components, but you can assume they're proportional to each other. And finally, when we analyze the periods, we're going to figure out exactly, if we get to this stage, maybe we won't have enough time, but we will analyze exactly what the proportionality constant is. And as we compute that proportionality constant, one is also going to notice that many curves get shrunk by e to the minus s. And this should already like be a red light in your head, because this is what's going to lead to a contradiction. In a hyperbolic surface, you cannot have many geodesics that are short. So in some sense, if my map is forced to shrink geodesics, the map cannot exist. Yeah. So that's what's going to happen. Like this conjugacy is going to be forced to shrink geodesics, and it's going to shrink so many geodesics that in the end, it's not going to be possible that it exists. That's sort of the main idea. Yep. Any questions? So the part that I want to focus on specifically is the first step, and then we'll see how much we can discuss about the other steps. But this first step has like a flavor that I like and that I find kind of nice, and it has to do with analyzing minimal sets. So let me remind you what the minimal sets of a flow are. The minimal sets of a flow, let's say E. This is again a general flow from a space X to itself. The minimal sets of a flow are the sets that are minimal for for the flow itself. So they are closed E invariant sets containing no proper closed E invariant sets. Yeah, it's a set that's minimal for D dynamics. It's a closed set that's minimal for D dynamics. And as you can see, a conjugacy, a topological conjugacy, should preserve minimal sets. It should be mapping minimal sets to minimal sets. So this is a concept that's preserved by a conjugacy. So it's a useful concept in our setting. And what's also useful is that we have a classification of earthquake flow compact minimal sets. And this goes back to work of Minsky, Smiley, and Weiss from 2004. And we need a very weak version of this classification. But before I mention what the classification is, let me do a very simple warm-up, and is think about what are the minimal sets on a torus. Yeah. So suppose you're working on the unit tangent bundle of S1 cross S1. So you have something like this. You have opposite sides identified. And now, after thinking a bit about it, I'm considering the flow that's just geodesic flow, linear flow on the torus. You can notice that minimal sets come in two flavors. They either come from rational orbits, say moving in this direction, you end up here, and then you end up here. So it's sort of a one-dimensional subtori, or they come from picking an irrational direction. Yeah, suppose I pick an irrational direction, and this orbit is going to sort of wrap around all over the place. And what I end up getting is just a two-dimensional torus with tangent vectors all pointing in the same irrational direction. So it's kind of natural that when you study minimal sets, you're going to see tori showing up in like subtori or tori showing up. And a similar thing happens for the earthquake flow. So we already saw something that resembled minimal sets, which were Fenchel-Nielsen twists. Yeah, if you twist along a curve, you get a periodic orbit. Now maybe you want to twist along two curves at the same time. Then you might not get an orbit that's closed because it's going to depend at the rate at which you twist, but you will still get a minimal set. And that's sort of what this classification tells you. So maybe let me say it here. A point x comma lambda in this bundle is contained in a compact minimal set if and only if lambda is a simple closed multicurve. Yeah. One of these directions is sort of easier, which is that direction. You just think about you're twisting about different simple closed curves. The only thing that has to be, its orbit closure has to be compact. Nothing, it has to look like a torus sort of. And the other way is the one that requires a lot more thought, and this is way harder. Yeah, but let me for now just use it as a black box.
So in particular, the only closed orbits come from multicurves. Is that right?
Yeah, yeah. In particular, closed orbits only come from multicurves.
I guess I didn't know that. That's okay.
Mm-hmm. Yeah, we expect something much stronger actually, but we expect that if lambda is not a multicurve, then the orbit is not, it's unbounded, like it escapes to infinity. But no one has actually written a proof down of that in the literature, so
okay,
we don't need to use it. Yep. Mm-hmm. Other questions? Okay, so let's say that we we call points of this form points that belong to a compact minimal set in a compact minimal set. We are going to call them bounded, just to give them a name. Yeah, if a point belongs to a compact minimal set, in this case, it's equivalent to its twisting locus being a multicurve. That's going to be what we call bounded. And what I want to think about now is, okay, so I want to think about the following. This shouldn't be here. Let's cut it up. So I want to think about the following. So I claim that already from the statement above this classification, we have this following corollary that if y comma mu is equal to f of x lambda, then lambda is a multicurve if and only if mu is a multicurve. Yeah. Again, this is just putting up what I said. We have a classification of compact minimal sets. They correspond to when your twist locus is a simple closed multicurve, and compact minimal sets are preserved under conjugacy. So this must be true. Okay, so that's one thing. But then we would like to go a bit finer, and that's to know if we can say anything about the number of components. Because with what we've said until now, there's not much that we can say. Can we say that lambda has the same number of components as mu? That's the question. And we're going to say yes, but the answer is going to be a bit more complicated, and it's going to have to do with the local topology of the set of bounded points near a given x lambda, say x lambda bounded. What do I mean? So consider the following question: how many ways can I deform a bounded point x comma lambda and stay bounded? Yeah. There are two things that I can do. I can vary the hyperbolic structure, or I can vary the twisting locus. So the hyperbolic structure plays no influence in if the point is bounded or not. So I can vary it however I want. So I get 6g minus 6 degrees of freedom there. I can vary the hyperbolic structure however I want. Now the point is, how much can I vary lambda? Can I vary a multicurve while remaining a multicurve? And this has to do with the number of components, yeah? Depending on the number of components, the answer is gonna be different. And for this, what I wanna do is look at the following picture. So this is an example where you have a multicurve with, on a genus 2 surface, a multicurve with 3 components and a multicurve with 2 components. So how many ways can I locally vary a multicurve with 3 components so that it stays a multicurve? Well, the only thing that I can do is vary the lengths, the weights. Yeah, I can weight them differently. So just by varying the weights, I get 3 degrees of freedom.
It looks like there's 3 on both pictures.
Oh yeah, so on the right-hand side, I just want you to consider the blue ones for now.
Okay.
Yeah, so on the left-hand side, we have 3 components, the 3 red ones, and the only thing that I can do is vary the weights. On the right-hand side, I want you to look at the multicurve given by the 2 blue curves. And again, what you can do is vary their weights. You can vary the weights, and that's going to give you 2 dimensions here. But you can do an extra thing to this multicurve and still remain a multicurve. And that extra thing that you can do is that you can add a new curve to this multicurve. Any curve that lives in this tori over here, let me just erase that, but in the tori that I shaded, any curve that lives here, you can add it to this multicurve of these 2 components with a very small weight. And the question is how many dimensions of curves you can add. Well, you can think that curves in this tori are completely determined by the number of times they spin in this direction and the number of times they sort of loop around this direction. Yeah, so in total, by varying the complementary curve, you get 2 dimensions of difference. Yeah, and so what's the difference then? Then here in total you had 3, and here in total you had 4 degrees of freedom. So what I'm trying to claim is that if you look at the local structure of the set of bounded points near any bounded point, that's going to determine you the number of components that the twist locus must have.
Sorry, I missed that. So where do you get the 2 for the green? You're saying there's 2 dimensions worth of green curves?
Yeah, so the green curves are determined by the number of times they twist along sort of they twist in this direction, or the number of times they go around. So that are the 2 dimensions.
Okay, and
so it seems like you're doing a little, you're making a small trick here, which is that really you only have a countable number of simple closed curves, but you have 2 dimensions of measured geodesic laminations. That's and the simple closed curves are dense in the space of geodesic laminations.
That's sort of what's going on behind, but
why can I not do the same thing for the red curves? I mean, I can change your A3, I can swing that through a countable family of nearby simple closed curves as well, can I not?
Locally, you sort of cannot.
Well, so you're just talking about homotopy, the the curve. That doesn't change the flows.
No, I don't mean homotopy. I mean change A3 to something that goes around A3 a million times and then goes once around the hole the other way. And
Yes. So maybe let me
Yeah.
say it this way: you cannot do that
you can't
with
do
an
that.
arbitrarily short path among curves. Like imagine
Oh.
if you're moving from an integer point to an integer point, sort of.
Yeah.
To do that, you sort of need to have you cannot do that deformation locally. That's what I'm trying to say.
Oh. I can't. Really?
Yeah, you can't. If you look at a connected component, let me say it in the technical words. If
Yeah.
you look at the space of measured geodesic laminations, it has this locus of weighted multicurves.
Yeah.
And what I want you to look is at the
Oh, I
connected
see. Okay.
component of a
Yeah.
tiny neighborhood of your point, and then you cannot access.
Okay, I think
It's not
okay. I see. So here on the right, you actually have sort of a legitimate two manifold plus sort of a star with countably many spikes and two dimensions worth of directions, like Lewis was describing.
Exactly.
And the other one, you really just have a three manifold.
Yeah.
There. So,
Exactly.
okay, I see. Okay.
Exactly.
Okay.
Yeah,
Okay, cool.
that's the exact picture. Yeah, and so let me see if there are any questions. Other questions? But the conclusion of this is that in the previous corollary here, we can actually know the number of components. So that sort of is showing us how we can reconstruct a lot of the information about this map. Yeah. So given the time that I have, maybe let me skip the step where let me tell you what the next claim would be. So the next claim would be to show that without loss of generality, if y mu is equal to f of x lambda, then lambda is proportional to mu. Notice that this is stronger than what we've shown. We've shown that the number for multicurves is mapped to multicurves, the number of components gets preserved. This tells you a bit more, like without loss of generality, you can preserve the same structure of any lamination, and there's this proportionality. This has to do with the curve complex, but for the sake of time, so that I can explain the conclusion a bit better, let me skip this for now. But this is also a fun step. I'm happy to tell you more afterwards, but it's also kind of funny and in how you use the curve complex. What you use is that any automorphism of the curve complex must come from a homeomorphism, which is a result of Ivanov. But then let me skip ahead and tell you a bit about periods. And the only thing I want to tell you about periods is explain that periods are very easy to compute. Yeah. And so what do I want to say about periods? So periods of simple closed curve twists can be computed in the following way. So if you're looking at the period of a point x and some weighted curve, the period is the distance that you need to progress, that's L gamma x, divided by the speed at which you're making progress, which is the weight. Yeah, very easy to compute periods of curves with one component. I claim that it's equally easy to compute periods of curves with two components. So maybe let me skip to this picture. This is periods of twists with two components. So the periods of curves with two components are equally easy to compute. So what's the period of x comma a alpha plus b beta? Well, it's what you would imagine. It's the least common multiple of having the twists work sort of independently by itself. So the amount of progress I have to make in alpha divided by the speed, and the amount of progress I need to make in beta divided by the speed. Yeah. So I claim that for these cases, the periods are pretty easy to compute. And now the claim that I won't prove for time reasons, but I just want to state it. is that if you play around, okay, let me mention one other thing about the periods. One extra thing is that your conjugacy F, so remember that this conjugacy had the property that ET composed with F is equal to F composed with E to ST. Just from that identity, you can see that it shrinks periods by E to the minus 2s. Yeah. So you know a lot about periods. You know periods of orbits where you twist along one curve, periods of orbits when you twist along two curves, and you know that your map shrinks periods. So you can play around with periods and start deducing a lot of stuff. And what I claim is the most important thing you can deduce is that if y comma mu is equal to f of x alpha, let me just normalize it so that it has length 1, and beta is disjoint from alpha, it's a simple closed curve disjoint from alpha, then what happens is that the length of beta is forced to shrink by e to the minus s. Yeah, this just comes from analyzing periods, and the part where the lengths become relevant is that they show up here. They show up in this least common multiple. And so you can, in some sense, show that if you're going to shrink by e to the minus 2s your period, the only way that can happen is that for disjoint curves, this is the identity bound that you get on the length. Yeah, let me ask you to believe that for a second, and just in the minute that I have, tell you how to conclude, because that's the funny part. You probably already guessed what I'm going to do, but the conclusion is sort of easy. So how can we conclude? So so I guess I have a picture down here. Oh yeah, I have it here. So look at the following configuration of curves. I claim that s must be equal to 0, else the following happens. You have y comma mu equals f of x comma lambda. And because of the previous claim, beta and gamma are disjoint from alpha. So then the length of beta in this new surface has to have shrunk by e to the minus s. And because gamma is disjoint from alpha, the length of gamma in this new surface has to also shrunk by e to the minus s. Yeah. Now keep applying this several times, iterate until the lengths of gamma and beta are so short that they contradict the corollary lemma. Yeah. You iterate it in one step, you shrink these two curves that are intersecting a bit, you iterate it again, you shrink them more, you iterate it a bit more, and then at the end, you get a contradiction. So the only way this could not be a contradiction is if there's no shrinking, which would mean that s would be equal to 0 here. Yeah, that's where I'll stop.
Yeah, so thanks, Francisco. Yeah, thanks, Francisco. Yeah, very nice talk. I'll just open it up for questions.
Well, I'd like to know about the, this shrinking of lengths statement that you didn't have time to talk about. If anybody else would like to hear that, but if somebody else has a shorter question, I could wait for that.